Hey guys, I'm Matt from the electrical team for McMaster Mars Rover, and in this video series, I'm going to show you how you can make your own power simulations for a Mars rover. So just a little background on what this project is. I had to create a simulation using Simulink to simulate basically the dynamics of the rover and the mechanical attributes of the drivetrain, as well as the electrical power consumption from the DC motors and our controllers. So in this series, I'm basically going to walk you through how to build your own power simulator. We'll be starting at the very basics, like how to use MATLAB and Simulink, and we'll be eventually getting up to actually building this entire model using Simscape, which is a library from Simulink. And then we'll actually get into using the MATLAB app builder as well. That will let you make a GUI for your application really easily. But that will be in some later videos. So this first video here is going to be just a quick introduction on how to use Simulink. It's not going to be a very thorough introduction. It's just going to be pretty simple. I'm going to show you how to basically model a wheel using regular Simulink blocks. If you want to learn more about how to use Simulink, you can just look up other videos that might explain it a little bit better. Also, another thing, if you want to see my final project or final product from before I made this series, you can actually go onto the GitHub. I'll put that in the description, so you can actually go there and grab those files and run it for yourself, see what the final product will end up being. And then I'm also going to be posting all of the files onto GitHub as well for each of the tutorial videos, so you can kind of grab the files as you go through different videos. And if you didn't want to watch the earlier videos, you can grab a later file and start working from there, and you don't have to catch up. So without further ado, I will show you how to work through Simulink. Okay, so I have MATLAB open here. As you can see at the top here, we have we have the working directory for MATLAB. So basically what you're going to do is to get to your working directory, you're going to hit this button and you're just going to navigate to any file that you're wanting to work in. So for me, we're doing simulation tutorials and we're doing part 1. So just open up that file folder, and you're going to want to have a separate file folder for any large project that you do. Because every file in there is going to share the MATLAB workspace, which is something that I'll go over in the next video. Okay, so to open Simulink, you press this button here. You can also just type in Simulink into the command window. All right, and this is going to look a little bit different from what you have. I just have that from a different class, this template. So you're going to go into Simulink, create blank model, and just give it a minute here while it goes. Okay, so now that you have Simulink open, what you're going to do first is you're going to save a file. And I'm just going to call this file wheel model. Okay. So with Simulink, basically what you're doing here is you're creating a model using blocks and signals that route from one block to another. So what I'm going to start with is a signal source. So let's go to Simulink, and we're going to go to sources. And from here, we are going to look for the step input. And we're just going to drag that and put it on our window. Come on. Okay. That's fine. Come on. Okay, I'm not sure why that's not working, but I'll show you a different way to do this instead. So you can actually double click on the screen and have the search bar come up, and you can type the block that you're looking for into the search bar. So it'll come up with step. So that is your step input. So basically what's happening here is from time 0 to some time that you specify in seconds, the input will be this initial value signal. And then your step time is 1. So after 1 second, it's going to jump to a input signal of 1. So you're basically just changing a binary value from 0 to 1, which is nothing too crazy right now. Another thing you can do here is you can change the stop time of the simulation. So the longer you make this, the longer it's going to take to run your simulation. So when you're doing small things, you just want to keep this time low, so you don't take as much computing power, um, or you don't have to just wait here for it to compile for a really long time. All right, next thing we're going to add is a scope. Scopes are really important for Simulink because this is how you're going to see the output of all your signals. To connect them, you just take the output signal from this block and connect it to the input of the scope. So now what's happening is your step input is feeding its output into the scope block. So what's going to happen is when you run this model, just let it compile and then run. Okay, so what you'll see happen is when you open the scope, just give it a second. All right, so when you open the scope, you can actually see the step input. So as I said from before, the initial value is 0, and it's going to stay at 0 until some specified time. So at 1, it jumps up to 1, and you can see it go until the end of the simulation. So the scope is basically just presenting graphically whatever signal input is being put into it. So another thing that we can do is we can define this step input as some physical value. So like I said, I was going to show you how to make a wheel model. So let's say we want our wheel model to have an input of torque. So we want to see how the wheel reacts with different step inputs of torque. So we're going to call this block torque. And let's say we want to try and get the angular acceleration to show up in the scope block. So going back to physics, the way that you get angular acceleration is by dividing torque by the inertia of the wheel. So what I'm going to do is I'm going to add a divide block. So Simulink is a little bit different than a lot of programming languages in that you actually have to create blocks to do your operations. You're not adding code or anything like that. These blocks are basically, they contain the code that you need to do your operations. Next thing we're going to add is a constant block. So a constant block is kind of like the step input, as in it's a source for a signal into the system. But instead of changing its value at a certain time, this is constant throughout the simulation. So we want to define this block as the tire's inertia. Okay, so the calculation for inertia of a wheel, we can just assume that the wheel is some ideal cylinder, and the formula for an ideal cylinder's inertia is just the mass times the radius squared divided by 2. So let's say our wheel weighs 0.6 kilograms and the radius is 0.1 meters. So we're going to square that. And then we're going to put this in brackets. I don't think you actually have to do this. I think MATLAB will understand what you're trying to do here with bed mass, but I'm just going to put the brackets there just to make it cleaner and divide by 2. Okay, so when you see this value C, it just means that the formula inside the block is a little bit big to show in that display, so you can just stretch it out until you see it. Okay, so that is the inertia for our tire. So then what we're going to do is we're going to route this signal into the divide block. So with the divide block, the top input here is basically the numerator for your division, and the bottom signal is your divisor. Okay, so so you can actually change how the inputs interact. So if you wanted to, you could do like a product. So you'd be doing multiply, so that would just multiply the two values together. But what we want is to take the top and divide it. So that is the operation to divide elements. Okay, So then what we're going to do is we're going to save and we are going to run the file. You can also run the file from inside the scope with this button. This is really helpful when you want to see the differences between scope outputs. Okay, so what we're seeing here now is the angular acceleration of the wheel, but this is in radians per second, because that is the output of like taking torque and divide by inertia using standard SI units. So we can't really tell what this value is. We know it's somewhere between 300 and 350. So a really important tool for scope is this measure tool. So you're just going to click on that, and once it shows up, okay. So what you can do here is you can move these target positions, or these little target points, and kind of choose where you want to measure. So on the side here, you can see that target position 1 is like at some time less than 1, and its value is 0, which is what we expected when you're feeding no torque into a wheel. It's not going to move. And then the second point reader here, we're just going to have that up after time equals 1. So we know that torque being applied there is 1 Newton meter. So 1 Newton meter acting on this inertia is going to give us an angular acceleration of that is 333.3 radians per second squared. So that is really fast, but ideally you would never be feeding 1 Newton meter into a wheel that small. That's pretty crazy. It's going to run pretty fast. So I'm just going to close this for now. Another really important thing that you can do in Simulink is you can actually label your signals. So this is really helpful later on, trying to keep track of where everything is, what signals are being fed into what, and what operations are actually doing in the physical realm. So here we're just going to call this angular accel. So this is the angular acceleration signal. So the values here are going to be of radians per second squared. Now say that we want to figure out what the translational acceleration is of this wheel. So if this wheel was an ideal wheel where there was no slipping, then basically just the acceleration, the angular acceleration times the radius will give us the translational acceleration of the wheel's center if it was rolling across the ground. So what we're going to have to do is we're going to have to multiply angular acceleration by the radius. So what we could do is we could add another one of these operation blocks and just make it a product block. But there's actually an easier way to do this. We can actually use a gain block. What a gain does is basically just multiplies the signal that is feeding into it by the constant that's on the inside, and then it'll output the signal on the other side. So from here, we're just going to delete this and connect these up. And from before, we said the radius was 0.1 meters. So we're going to multiply angular acceleration by 0.1. And I'm just going to name this as well to radius so we can keep track of it. And that means this output signal will be translational accel. Okay. So spread that out so it's easier to see. All right, and then we can look at the scope again, run the simulation. All right, and we can see from the measurement window that this is now translating, is a translational acceleration of 33.3 meters per second squared. So that's extremely fast. That's way faster than any wheel should be accelerating on the ground. So let's change this torque. We're actually going to change this down to 0.05 Newton meters, which is a bit more realistic of a value for a wheel like this. Okay, so we're just going to run this again and see what that did. Okay, so now we can see that the output is around 1.6 meters per second squared, which is a lot more reasonable acceleration. Now let's say that we wanted to find out the velocity of this wheel. Like how fast is it moving along the ground? So to do that, we know that acceleration is just the derivative of velocity. So in order to go from velocity to acceleration, you take the derivative. But to go backwards from acceleration to velocity, you have to take the integral. So there's actually an integrator block. It looks like this. So 1 over s. If you don't know what that means, don't worry about it. It's not that big of a deal. It's basically just a Laplace transform for an integration operation. So I won't go into exactly what that means, but all you have to know is that it's just taking the signal that's being inputted into here, and it's going to take the integral of the entire thing. So now the output here is actually just the velocity. So now that we have an input torque going into the wheel, and we are integrating it into velocity. So before we saw that it went from one constant value up to another constant value, the acceleration. So by going from a constant acceleration to a velocity, we should see like a constant slope velocity that's going from 0 to whatever value it's going to be accelerating up to. So we're going to run this and we're going to check the scope. Okay, so we know that this is correct because we see we're starting at 0 before the torque is applied. Once the torque is applied, we start accelerating, and that is when we are changing at constant speed, or changing speed at a constant slope. So you can move your pointers along any part of this slope. And another thing that you can do too is you can move this other first point to some point on the slope, and you can actually look at this delta y value. This is your your change in velocity between these two periods. So that is 2.3 meters per second. And you actually have a delta y over delta t. So that is just your slope. So remember before our acceleration was around 1.6 meters per second, or meters per second squared. Well, this slope is 1.667 per second. So you're going to multiply any velocity by this slope, and you'll get the acceleration, or any range of velocities by the slope, and you get the acceleration. Okay, so we're going to close this. Now, let's say that you wanted to get the position of the wheel along some plane. So you've got this wheel rotating, and it's starting to accelerate, and it's moving, and you want to determine how far it gets in 4 seconds. So what you're going to do now is, because velocity is actually the derivative of position, you're going to add another integrator block. And this is going to give you position. So you're just going to delete this velocity output, put it in here, zoom out and move over. Move this stuff over. Okay. And this is position. Okay. So that looks pretty good. We're just going to save the file and run it again. So at constant acceleration, position should be changing at a parabolic rate. So we should see, yes, okay. So we see a parabolic change here. Position. So you can move this cursor. So if you wanted to see what the position was after a simulation of 4 seconds, which is only an acceleration of 3 seconds because we're starting the step input at 1, we're going to change this and just move it right to the edge here. And we can see that we are getting up to 7.48 meters. So we went from 0 to 7.48 meters in 3 seconds, which is pretty fast. And it's a very good way to get us started on using position and acceleration to determine power usage. So another thing that you can do is these scope blocks can take multiple inputs. They don't just have to take one. So to add another input, you just kind of have to hover your mouse below your other input until you see this little crosshair and click and drag, and you can actually add another signal input. So let's say you wanted to check out what the translational acceleration was in comparison to the position. You can run this again, and it will actually map the acceleration and position together. So this blue line here is the acceleration, and the yellow line is the position. And then you can change measurements by going up to this trace selection and changing to translational acceleration. So as long as you have your signals named, these signal names will show up and you can choose between them. Otherwise, it'll just kind of show up as like, it'll say like the output from a certain block or whatever, which is a little bit confusing sometimes. So this is a good reason to always name your signals. So it's a lot easier when you're looking at the scopes. Okay, and the last thing, actually I'm going to, I'm actually gonna leave that. Okay, so the last thing we're going to do is I'm gonna show you how to make a subsystem. So a subsystem is basically like making another Simulink model within your Simulink model. It sounds a little confusing, but it's actually super helpful to make everything a lot cleaner. So I'm just going to show you how to do that. So you're just going to click and drag and bring this box over everything that you want to go into your subsystem. So what I'm going to try and do is I'm going to put this entire wheel into one subsystem. So you're going to right click once everything is selected and create subsystem from selection. Okay, so now this subsystem is our wheel. We're going to call this wheel. So we're inputting a torque into this box, and this box is going to output the position and translational acceleration of the wheel. So we can actually go into here. Let's name this signal torque just to make everything clean. And we can actually go to this block here and change the port name to the signal name. That way, when we leave the model, this now says torque instead of 1. So we know that torque has to be inputted into here, and then position and translational acceleration will be outputted. So by double clicking on the box, you can go into it and you can see the entire system that you had before. So this is the wheel model. And then when you exit the wheel model, now you have a block called wheel. So you just input some value and it'll output some values. So this just, you can use this to make your models a lot cleaner, easier to navigate, and a lot smaller. So you can take a really big model and just kind of compact it down into like a few blocks and make it really easy to see, really easy to show people, easier to understand. So I'll just go to the scope block and just show you that everything is still the same, nothing changed. Perfect. Except that it did say that the output is coming from the wheel block, which is okay. That's just because I don't have these signals named. So it's just telling me that it's coming from the wheel block and the output is the translational acceleration. Okay, in the next video, I'm going to show you how to use MATLAB variables in Simulink and how to create MATLAB scripts to actually edit those variables. It's very helpful when making really large projects. So if you need to grab this model, make sure to check out the GitHub to get the code. And yeah, I'll see you in the next video.